Now, in section 4, we come to some problems on analytical functions. So, we already know the conditions of Cauchy-Riemann equations and analytical functions and holomorphy and the singularity of a function in the previous slide. We come to the problems, some few problems. So, similarly, we can do an existing problem in the textbook. So, under original problem and the specific problem, we can try the similar way. Only a few examples on the problem will be there. So that the function f of z equal to sin x cos h y hyperbolic function y plus I cos x sin hyperbolic function y is continuous as well as analytical everywhere. So first we take a given f of z equal to sin x cos hy plus I cos x sin hy. We express this term should be equal to u of xy plus I v of xy. So we are selecting in the u of xy as a real part of xy plus I times of v of xy is imaginary term. So separating real and imaginary term. So we express u of xy equal to sin x cos hy, v of xy equal to cos x sin hy. Where u and v are both the rational functions of x and y given non-zero denominator for all values of x and y. Therefore, u and v are both a continuous everywhere, hence f of z is continuous everywhere. So, a function u and v are continuous, the function u and v are continuous, and when its function is continuous, where u and v are continuous. Now, so differentiate partially with respect to x, we get w by del x equal to cos x, cos hy. So, derivative of sin x is cos x. Again, w by del y differentiate. So sin x as it is, derivative of hyperbolic cos hyperbolic function is sin hyperbolic. So w by del y equal to sin x sin hy. Again, dw by del x is minus sin x sin hy. Del v by del y equal to cos x cos hy. We are differentiate partially between v with respect to x and with respect to y. We get minus sin x sin hy and cos x cos x. Now, I compare it here. What the Cauchy-Riemann equation say? So, del u by del x equal to del v by del y. Del v by del x equal to minus del u by del y. So, here u and v satisfy Cauchy-Riemann equation. Thus, f of z is analytic everywhere. We come to the similar one more example. So, that f of z x equal to xy plus I y is everywhere is continuous but not analytic. So continuous is not analytical means is not satisfied the Cauchy-Riemann equation. It's a given solution. C1 f of z equal to xy plus iy. So again I separating real and imaginary term u of xy plus I v of xy. This implies u of xy equal to xy, v of xy equal to 1. Again u and v are a polynomial in x and y, therefore they are continuous at each point. Hence, f of z is everywhere is continuous. Now differentiate partially u with respect to x, partially with respect to y. Now del u by del x equal to y, del u by del y equal to x. Again, del v by del x is 0, del v by del y equal to 1. So differentiate with respect to y, we get the 1. Again, the del u by del x is not equal to del u by del y. So because here y we get is constant is not. Again, del u by del y is not equal to minus del v by del x. So that Cauchy-Riemann equation is not satisfied. Hence, the problem is not analytic. But the function is continuous. But the CR equation does not satisfy. One more example, I said that for what values of z, the function w defined z equal to u e to the power of minus v or cos u plus I u, where w is equal to u plus iv, cases ceases to be analytical. Means, if we take one more additional is given, if we differentiate z with respect to w, because z and w is a function in a complex derivative function. If we take z differentiate the same function we are expressing that dz by dw expressed in del u del z by del u equal to e power minus p minus sin u plus I cos u, because differentiate with respect to u in the right, e power minus b derivative cos u minus sin u plus I times derivative sin u is cos u. I take I as the outside. I take so I is equal to I into e power minus b cos u plus, again I can express because I taken outside, so you take I square is minus 1. Instead of that, you can take 1 times I on the outside, we get plus I times of u. Because I square is minus 1. Instead of minus 1, I taken I square minus 1. Instead of I square, we can take minus 1. So I take 1 I in the outside, I write this equal to I z. So I z. So dw by dz equal to 1 divided by I z. I take one reciprocal of that, we get that. So for w to be an analytic function, dw by dz it should be a finite. So w is to be analytic if z equal to 0. So one more example I get now. For what values of z do the function w defined by z equal to sin hyperbolic function u cos v plus I cos hyperbolic function u sin v. W equal to u plus iv, this is to be analytic. So the same way you are expressing that is given in the previous problem form. So we have dz divided by dw is equal to del z by del u. So equal to differentiate with respect to u. So sin hyperbolic function is cos hyperbolic function. Yeah, differentiate cos hyperbolic function. Yes, sir. Sin hu become cos hu cos v plus cos hu becomes sin hu sin v. So differentiate with respect to u, we get cos hu cos v plus I sin hu sin v. Again, we now take z square. If we z square, we can subscribe that term. We equal to sin square sin hyperbolic square u cos square v minus, because I square is minus 1 minus cos h square u sin square v plus 2 times of sin 2 times of I sin hyperbolic function u cos v cos hyperbolic function u sin v. Again, we are collecting that. If we take a cos square v as a common, we get sin cos square h v minus u times of cos square v minus of 1 plus sin hyperbolic function of square u into sin square v plus 2 times of I sin hu cos v cos hu sin v. Because I am using that. Because here cos square theta plus sin square theta is equal to 1. In the hyperbolic function, cos square hu minus sin square hu h square 2 equal to 1. By using that formula, again I using that formula, we get that this term should be equal to cos hu sin v cos v plus sin hu sin v minus 1. So again, this term we can write dz by dw whole square minus 1. This is the, we are expressing this term should be equal to dz by we are differentiating that. The differentiating dz by dw is equal to cos hu cos v plus I sin hu sin v. So you will write dz by dw whole square minus 1. Or we can write dz by dw whole square is equal to z square plus 1. Taking minus 1 this side, we get 1 square. Or dz by dw is equal to plus or minus square root of z square plus 1. Or taking reciprocal, we get dw by dz is equal to plus or minus 1 divided by root of z square plus 1. For w to be analytic, dw by dz should be a finite. Therefore, w is to be analytic if z square plus 1 equal to 0 or z equal to plus or minus I. Because we are taking 1 this side, minus 1, we can write complex form, we can write that is square root of minus 1, square root of minus 1 is I. So z square is plus or minus I. So in the same way, we come to one more example in the regarding the derivative. So that f of z is sin z is analytic and derivative of sin z is cos z. So same way we are expressed in terms of Cauchy-Riemann using the Cauchy-Riemann equation. So f of z equal to sin z. So z here is a complex number. We write z can be written as x plus I bar. So sin of x plus I bar. What's the sign of a plus b formula using sin a cos b plus cos a sin b, like that? We write sin x cos I bar plus cos x sin I bar. Again we write sin x cos I y is cos hyperbolic function of y plus I cos x sin I y is cos a sin hyperbolic function of y. Again we are separating the real and imaginary parts, so we can write u of xy plus I v of xy, where u of xy is sin x cos hy, v of xy is cos x sin hy. So differentiate partially with respect to x, we get derivative of sin x is cos x, as cos hyperbolic function keep as it is. We are differentiating this as partially. Again, del u by del y. So again differentiate cos hyperbolic function, we get sin hyperbolic function. We get sin x sin hy. Again we come to the v function, del v by del x equal to minus sin x sin hy. We are differentiate cos x, we get minus sin x. Again del v by del y, we get cos x cos hy. Now we compare the Cauchy-Riemann equation. Del u by del x is equal to del v by del y, and del u by del y equal to minus del v by del x. Here Cauchy-Riemann equation are satisfied. Further, del u by del x, del u by del y, del v by del x, and del v by del y are continuous functions, and f of z equal to sin z is analytic. One way is true. This satisfies the Cauchy-Riemann equation. We come to the further, what the derivative in that is to be expressed in the partial derivative conditions. So by applying the differentiation by definition, derivative definitions, by applying the derivative definitions, we already know this definition in the previous slide. So f dash z equal to del u by del x plus I del v by del x. So this equal to what's the del u by del x? Del u by del x is cos x, cos hyperbolic function of y, plus I times of del v by del x is minus sin x sin hyperbolic function of y. So again I open this cos x cos hyperbolic function of y minus I times of sin x sin hyperbolic function of y. Again cos x cos hy can be written as cos hy can be written as cos hy. Again minus sin x sin hy can be written as sin hy. Again we are collecting that cos x cos hy. Instead of I can write, so this sin x minus of minus, so sin I bar sin I bar, that I write this is the minus 1 equal to I square equal to minus 1, this is the plus sign. So sorry, I taking this is a plus sign. So we get cos of x, we are using cos a cos b minus sin a sin b formula. Cos a cos b minus, because this is I square, we get that. I square is minus 1. So minus of minus we get plus 1. So we get, so here this term, I think this is a positive. This become I square. So hide that here. So this is up. So this become a negative. This negative cos x cos I by minus sin x sin I by. This is formula for cos of a plus b formula. Cos a cos b minus sin a sin b formula. So we get cos of x plus I by. What the cos of x plus I bar is complex numbers that we can cos of z. So derivative of sin z is cos z, means f dash of z equal to cos z. Now we come to the one more example regarding in the log z formula. Still, so that f of z equal to log z, f of z equal to log z is analytic, and hence derivative of f of z equal to 1 by z. The same way we are like, so let f of z equal to log z. So z x plus, so log of x plus I bar. Again we are separating u of x square plus iv of x square, is separating that. So we get 1 by 2 log of x square plus y square plus imaginary term plus I times of tan inverse of y by x. Yeah, again this is first real and imaginary term u of x square plus I v of x square. where u of xy is 1 by 2 log of x square plus y square. Then v of xy is tan inverse of y by x. Here, again, we are differentiating partially with respect to x. We get del u by del x equal to x, differentiate this. So 1 by 2 as constant, derivative of log form. 1 by x square plus y square. Again, derivative of x square is 2. Here, 2 get cancelled. We get x divided by x square plus y square. We come to the del u by del y. Again, 1 by 2 as constant. One derivative of log is 1 by x square plus y square. Again, derivative of y square is 2 by. So 2 get cancelled. Y divided by x square plus y square. We come to the v form. Del v by del x. Again, derivative. Tan inverse of form. 1 divided by 1 plus y square divided by x square. Again, derivative of x square, y square by x square. We get minus y divided by x square. Because we are differentiating with respect to x, y square are common. Again, this becomes minus y by x square. We get it. So again, is simplifying here. The LCM is x square plus y square. X square gets to numerator. We get the x square get cancelled. So generally, we get minus y divided by x square plus y square. Again, del v by del y. We get a differentiate with respect to y. 1 divided by 1 plus y square by x square. Again, derivative of that y by x with respect to y. 1 by x per form. We get derivative of this. We get this 1 by x. Again, this gets x divided by x square plus y square. Observe that this satisfies the Cauchy-Riemann equation. Del u by del x is del v by del y. Del u by del y is minus sign of del v by del x. Hence, the Cauchy-Riemann equations are satisfied. Further, ux, uy, vx, and vy are continuous functions. Hence, f of z equal to log z is analytic. Further, we come to the derivative form. So this is one day we are expressing this in analytic condition, also expressed in the definition of derivative condition. This is a definition of derivative condition. Derivative of f of z equal to, by definition, del u by del x plus I del v by del x. So del u by del x we already simplify. Y minus y divided by, what the del u by del x is? X divided by x square plus y plus I times of, what's the del v by del x? Del v by del x is minus times of y divided by x square plus y square. Again, simplifying. So x square plus y square as LCM. So x minus I bar. Again, further that derivative of. So in the denominator, we are x square plus y square. You are expressing x square plus y square as x minus I bar into x plus I bar, because it is product here. So x minus I bar divided by x minus I bar into x plus I bar. So x minus I bar get cancelled. 1 divided by x plus I bar. So 1 divided by x plus I bar. So 1 divided by z. Z is complex number we can do. Thus, derivative of z log z is 1 by z. Means f of z is log z. Derivative of z is 1 by z. So this is the way your problem we are simply doing. So analytical way. So analytical way means if a function is given, they satisfy the Cauchy-Riemann equations, also satisfy the definition of derivative conditions. So see one more example. We come to the complicated. Complicated means not a complicated. So this is the way we are proving the way, so that if f of z is u plus I bar is analytic, then so that dou by dou x of f of z whole square plus dou by dou y of f of z whole square is equal to derivative square. See, so one way here, so f of z is analytic, so we are proving. So f of z is u plus iy, so f of z square is equal to u square plus v square. Suppose we are taking. If we differentiate partially with respect to x and y, we get. So at left hand side, I differentiate in this part. So what you get? 2 times of absolute values of f of z with respect to x, dou by dou x of f of z. Again, 2 times of in the right hand side, 2 times of u dou u by dou x plus 2 times of v dou v by dou x. I call this equation as 2. Again, so 2 times of mod f of z dou by dou y of f of z is equal to, we are differentiating with respect to 2u dou u by dou y plus 2v dou v by dou y. So I call this two equation as 2. So again, I come to the left hand side by using Cauchy-Riemann equation. 2 times of f of z dou by dou y of f of z is equal to, so instead of dou u by dou y, I express in terms of dou minus times of dou v by dou x plus 2v of, again, dou v by dou y equal to dou u by dou x. I using the Cauchy-Riemann equation. So squaring and adding 2 and 3, we get, yeah, 2 times of this, we get 4 times of mod f of z whole square dou by dou x of f of z whole square plus 2 times become 4 times of f of mod f of z whole square dou by dou y f of z whole square is equal to, in the right hand side, I take for 2 we get 4 u square, 4 u square we get, I take 4 plus 4 v square, I take 4 as a common, u square plus v square, as that at the simultaneously dou u by dou x plus dou u by dou y, we get dou u by dou x whole square plus dou v by dou x whole square. Again, but mod f of z equal to u square plus v square in the equation 1. So I use this equation 1. So dou by dou x of mod f of z whole square plus dou by dou y mod f of z whole square is equal to 4 times of u square plus v square as mod f of z whole square. This and the left hand side and the right hand side get cancelled. My 4 mod f of z whole square. The left and the right hand side of 4 times of this does get cancelled. We get dou by dou x of mod f of z whole square plus dou by dou y of mod f of z whole square is equal to dou u by dou x whole square plus dou v by dou x whole square. Call this equation as 4. By data, f of z equal to u plus ib is analytic, therefore derivative of z is exists. See, analytic means the function is derivable. The function is derivable. So derivable exists, suddenly the function derivative of z is exists. And derivative of f of z is dou u by dou x plus I dou v by dou x. That is, this implies absolute values of derivative f of z is equal to dou u by dou x whole square plus dou v by dou x whole square. Now I am comparing 4 and 5. See, observe in the equation 4 and 5. So we have dou by dou x of mod f of z whole square plus dou by dou y mod f of z whole square is equal to derivative of mod absolute values of derivative f of z whole square. See, you observe equation 4 and 5. Observe equation 4 and 5. Here, right hand side are equal. So suddenly we can write absolute values of derivative of the whole square should be equal to dou by dou x of absolute values of z square plus dou by dou y of absolute values of f of z whole square. This is true. This is exists. So this simple problem we are doing, and in the way. In this way, we are exercising all in the textbook problems. In the given textbook problems, we work out. So we get it. The function is continuous. The function is analytic. The function is variable. The function is in the same way in the form of problems. We can